Hi everyone, here's another video about the CSS Pure Mathematics Exam from 2023. We are still in section B, and this is question 6, item A. So it asks us to evaluate the double integral of the function x squared plus y squared over the region bounded by the curves given by xy equals 1, y equals 0, y equals x, and x equals 2. So first, let's sketch the region. So here we have the region. So here we have the curves y equals x, this line here. We have the vertical line x equals 2. We have the horizontal line y equals 0, which is just the x-axis. And we have this hyperbola, which is the curve xy equals 1. So the region we want to find, over which we want to integrate, is this gray region here, which I call R. So now, once we know a bit about how is the region, we must find these points here, these intersection points here, this one, this one, this one, and this one. And this will allow us to describe the region algebraically, and so we can proceed with our integration. So we will need to find these points. And as we'll see, they are easy to find. So let's go. So first, it's easy to see from the picture that the vertical line x equals 2 intersects the curves xy equals 1 and y equals 0 at this point here, 2, 1/2 and 2, 0, because if x equals 2, if I want the point xy to be in the curve xy equals 1, y must be 1/2. So 2 times 1/2 equals 1. And if x equals 2, if I want to intersect the line y equals 0, the only way is for the point to be 2, 0. So I already have 2 points. Now, it's easy to see that x equals y intersects the line y equals 0 at 0, 0, because since x must be equals y, when y equals 0, x must be 0. So this is fine too. Now for the last part, I want to see where the hyperbola x y equals 1 intercepts the line y equals x. So this is also easy. I take a point xy, since it must be in the line y equals x, the point must be of the form xx. And since I need xy to be equals 1, I need that x squared equals 1. So this gives us that x must be either 1 or minus 1. But minus 1 is not a point which suits us. It's not a value useful to us, because from the drawing we can see that R is in the first quadrant. So all x's must be positive or 0. So we must have x equals 1, which gives us that this point must be 1, 1. Perfect. So now we have these points, and we are ready to proceed in order to describe this region R algebraically in order to integrate. So here we go. Here I have 2 pictures, and I'm gonna comment more on the pictures than on which is written here. So first I take, as we know that this point is here is 2, 1/2. If I take any y0 greater than 0 and smaller than 1/2, or smaller or equal than 1/2, and I consider the line y equals y0, which is, for example, this red line here, I can see that the line intersects the region R starting from, it enters the region R from x equals y0, and it exits the region when x equals 2. So we can describe the intersection of this red line with this region as I have written up here. So it's the set of points xy where y equals y0 and x is greater or equal than y0 and less or equal than 2. And now if I take some y0 greater than 1/2 and smaller than 1, smaller or equal than 1, like we have here in this red line, and I take a horizontal line y equals y0, I can see that this line enters the region and this point here, which is given by y0 because it is in this line x equals y, but it exits the region in the hyperbola. The point at which this line, red line, exits the region is in the hyperbola. So it's a point of it's 1 over y0. And so I can describe this intersection, this line segment here, this way. So it's the set of points x, y, and R2 such that y equals y0 and x is greater or equal than y0 and less or equal than a half. And with these two observations, I can see that I can break the region R in two subregions. I have this part here, which is below the line y equals a half, and the part which is above the line y equals 1/2 and below the line y equals 1. So, and this is what I'm going to use to integrate. So I can describe the region this way. So we have a R1, which is the set of points where y is greater or equal than 0 and less or equal than a half, and x goes from y to 2, and I have a second part, R2, where y is greater or equal than a half and less or equal than 1, and x is greater or equal than y and less or equal than 1 over y. Now, once we know this, the function we wanted to integrate is continuous, the region is bounded, and it is a compact region, so we can integrate and use Fubini's theorem. So let's do this. So the integral we want is this one, and now from now on we only have to make calculations. So we can write this integral as the sum of the integral over the two regions R1 and R2. And now we can integrate. So we can rewrite both integrals as iterated integrals. So for the first one over R1, we have that x, that we know that y goes from 0 to a half. So we have here 0 and a half. And here x goes from y to 2, and in this, for the second integral, y goes from a half to 1, and x goes from y to 1 over y. So now we're just calculating here. We just find a primitive of x squared plus y squared with respect to y. We're applying the fundamental theorem of calculus. So we have this expression, and making the substitution, we obtain this. And now we only have to solve integrals over y. So we integrate again, and again using the fundamental theorem of calculus, and I have to substitute this here, and now it's just calculations. So I plug in the numbers, and we get 47 over 24. So it's not a hard problem. The most difficult part is describing the region algebraically. So I hope you enjoyed the video. I will make more videos soon. Thank you very much for watching. Please subscribe to the channel, give me a thumbs up, and let me know your thoughts on the video. Thank you very much. Bye.